Europe. Well, end of the conference. I hope it was a really good one. Now, if you meant to go to some lightweight talk at the end of the conference, you are at the wrong place, because this is going to be heavy. I had to warn you. So, my name is Vlad Khononov. You can call me Vlad or Vladik. Last name, I don't care anymore. At this point of time, you can pick any Polish last name for me and just call it. I'm fine with that. I am a software architect. I specialize primarily in distributed systems and domain-driven design, speaking of which, this is my latest book. Has anybody here already got it? Oh, we'll get there. Okay, we see some hands. Rest of you, you know what to do, right? I don't have to say it aloud. Just kidding. By the way, there is a Polish translation, and one shop here in Krakow has it. And whoever is going to buy that book, they're going to discover a little surprise that I left there. However, it's not on the first page, so you will have to really go and read it like you really mean it. Anyway, so today we're going to talk not about domain-driven design, but another subject that I'm really, really passionate about, and that's coupling. That's the topic of my upcoming book, which was supposed to be published a year and a half ago, but I'm a software engineer, which means I'm bad at estimates, so don't blame me for that, part of our job. Anyway, I hope that I will finish this book before it finishes me. Right now it looks like it is going to finish me, but I'm doing my best. Anyway, I want to give you a preview of this book's material. Now, this is not going to be a teaser, just to raise some interest and tell you to get the real stuff, you have to buy it. No, you will get some real tools that you can use in your day-to-day job. Now, as I said, this is going to be a heavy talk. We have to cover a lot of material. I'm not sure we're going to have time for Q&A. If we do, then awesome. If we don't, I'll be around here. And whoever is going to ask the most interesting question is going to get a copy of the Monkey Book. And with that, let's proceed. So here's the thing. Lately, there is one quote that lately I've been including on all of my presentations. And this time, I was thinking, hey, why should we wait till the end or the middle? I'll put it right there on the first slide. So here it is. Ruth Milan, she says, system design is inherently about boundaries. What's in, what's out, what spans, what moves between, and it's about trade-offs. It reshapes what is outside just as it shapes what is inside. And I wanted it there on the first slide because it outlines the overall topic of this presentation, system design. And more specifically, the relationships that span across boundaries of modules or components or whatever. Relationships that involve the thing that we fear the most, coupling. And we've always been told that coupling is bad. Coupling slows us down, it cripples our systems. When working on a code base that resists any changes we want to make, we blame it on coupling, of course. As a result, not surprisingly, what do we want to do about coupling? We want to terminate it. We want to decouple everything. We want to break everything apart into tiny, tiny classes or microservices or serverless functions, whatever. The motivation is always the same. We want to be able to change every one of those little boxes independently. But when focusing on size alone, what results are we getting? Well, in many cases, we go from coupled piles of code to decoupled piles of code. That's not surprising. As my friend Matthias says here, going for as small as possible is almost universally a bad advice in software design. Also, Nick Thune says, there are many useful and revealing heuristics for defining the boundaries of a service. Size is one of the least useful. Yet, we keep on doing that. So, I know it may sound controversial, but instead of fighting coupling, in the next 45-ish minutes or so, I want to show you a different way of thinking about coupling And I will even try to convince you that you can use coupling as a design tool, a tool that can help you to design modular systems. So this is our agenda. We're going to start by defining what coupling is. What is this thing that we call coupling? What is it exactly? Then we're going to explore the dimension of coupling, or in other words, the different ways coupling manifests itself in software projects. Finally, we are going to combine that knowledge into a framework that will allow us to use coupling as a tool for designing modular systems. So what is coupling? If we go to the lexical origins of this word, it will take us all the way back to Latin, where it was composed of two words, co and apere. Co-apere meaning fastened together. In other words, if two things are coupled, it simply means that they are connected. And that makes coupling pretty much a ubiquitous phenomenon. It is everywhere. This clicker, it is coupled to my computer. Organs in our bodies are coupled to form us, living organisms producing code, or stress hormones in my case right now. Anyway, cars, computers, cities, organisms, companies, or any kind of system is held together by coupling. You cannot build a system out of disconnected components. This is just a collection of some parts. Simply grouping them together in some boundary doesn't make it a system. It's just a bunch of fully independent and fully decoupled entities. But again, that's not a system. For a system, we need those relationships, these connections between these components. Coupling, as a result, it makes that overarching system greater than the sum of its parts. It produces value. We produce value by connecting those components together so that they can achieve another overarching goal. Therefore, it makes no sense to try and completely decouple everything. So that makes coupling an inherent part of system design. So instead of trying to eliminate it, it's more reasonable to evaluate those inner component relationships and see if they're working for us or against us. And if they are working against us, see how we can adapt the design of a system to reverse that. Now, let's see a quick example. Let's say we have two coupled components. This downstream here on the right, it references and thus depends on the upstream component on the left. The arrow between them, that relationship, it defines how these components are integrated. It defines how a change in the upstream component is likely to break the integration and require cascading changes in other parts of a system. As Michael Nygaard says, coupling defines the components' degrees of freedom, how freely the components are able to change without affecting other parts of their systems. In other words, coupling defines what changes can we make in the upstream here without being afraid to break integrations with downstream components, other components that depend on it. The interfaces that are used for integration, they have to enable some movements or changes, but they also have to prohibit others. Now, this prohibiting thing, I know it sounds limiting, but actually we don't want unlimited degrees of freedom. That will render any system overly complex or simply unusable. For example, I don't want this clicker to be coupled to my phone or a car or that chair for that matter. It makes no sense. Unlimited degrees of freedom is chaos. It's another opposite of a system. So instead, what we want to do is make some integrations and changes safe while restraining those that we are not interested in. We want to align the allowed degrees of freedom with our needs and expectations of future changes in the system that we are designing. So that makes coupling a first-class design decision. So going back to Ruth Milan's quote, we want to design what spans and what moves between the boundaries in a way that enables only the changes and movements that we actually need. Now, to do that, we have to understand how coupling works, the dynamics of coupling. And the thing is, coupling is not some simple unidimensional phenomenon like usually people tend to describe it. It's more complicated. It affects system design in multiple dimensions, in the dimensions of space, time, and the combination of these two, the gravitational force that pulls them together. Let's go over them. I'm going to start with strength, and that's going to be a heavy one. That's where we're going to spend the most of our time. So, the effect of strength is probably the most obvious. It reflects a sort of gravitational force that pulls components together. It defines what is the impact of a change in one place in a system will be on its other components. The higher the strength, the more cascading changes will follow. And as our industry evolved, a number of models were introduced to evaluate strength, namely coupling in a methodology called structure design and a model called Kinescence. Anybody here familiar with structure design? Oh, I see one hand. Awesome. Kinescence? One hand as well. Awesome. You rock. For the rest of you, let's go over these models. Now, I will really go briefly over these models, and please don't try to memorize all of this stuff. You don't need that. Instead, try to focus on the levels of these models and try to see what is the difference in terms of implicitness or explicitness of interfaces, how predictable they are, and how easy they are going to be to evolve if needed. And most importantly, try to focus on what kinds of knowledge are being shared by different levels of these models. So, structure design. This methodology was coined back in late 60s, but it got really popular in early 70s. And these two books, you're not going to find them on Kindle, but it's really funny that if you open at least this one, the red one, they describe problems that software engineers are facing and how to address them. And if you ignore the date, the publishing date of the book, it really sounds like it was published today. So back then, to evaluate coupling, they proposed these 6 levels. Content, common, external, control, stamp, and data coupling. Now, of course, these terms sound pretty unintuitive for us, and that's because they are based on languages such as COBOL and Fortran. Luckily, we are not using them, so let's see what they mean. The first one and the strongest level of structure design's coupling is called content coupling. And the idea here is simple. A module uses private interfaces, or in other words, implementation details, to communicate with other parts of a system. Now, back in those days, an example, a poster boy example of content coupling would be go to statement. Go to line number something. That means you know exactly what is written on that line. And if, God forbid, that line changes, your module is going to be broken. It won't work anymore. Now, luckily, we are not doing such defined stunts nowadays, but we still have our ways. For example, reflection. If you are working with C#, Java, I don't know, other languages, you can use reflection to access private fields or to execute private methods. They were not intended for integration. So in that sense, that's still content coupling. Next one is common coupling. And here we have 2 modules that communicate through a globally accessible memory space. This shared memory space is an unstructured global byte array. Both modules have to duplicate the knowledge of how that data in that global memory is structured. There is no formal integration protocol that is being enforced by any of these sides, which makes such integration interface quite implicit. Now, in those days, that was just global memory. That's it. Today, again, we have our ways. For example, let's say you have 2 services that communicating with each other by updating a file, an object in S3, for example. They both have to hold that knowledge of how that data in that file is structured. If one of them decides to change that structure, well, they better communicate that with the second team, because otherwise the system won't work anymore. So again, we have some shared memory, and it's not properly documented. It's quite implicit. Slightly lighter level is external coupling. And here, instead of focusing on unstructured memory space, the modules are sharing a global variable. That variable may be a primitive or an array of primitives, but it's still shared memory. But again, at least here, the interface is more documented and it's a bit more explicit. Next level is called control coupling, and that's the most fuzzy one. This one happens when one module dictates to another one how to do its job. For example, when you have business logic that is not properly encapsulated in one module, but it's spread across two modules. That's an example of control coupling. Stemp-coupled modules are communicating by exchanging data records. These data records or data structures, they contain more information than is actually needed for integration. Let's say there is a CRM module and I'm asking it, please give me an email address of a customer. And instead of giving me the email address, I'm getting a whole data structure with let's say, dozens or hundreds of different fields. Well, that's fine. I will find my information there, but sharing that extraneous information, it makes downstream components more and more sensitive to changes in the upstream components' internal data structures. And finally, we have data coupling. This is the lowest and the most desirable level in structured design. Here, the modules are communicating by passing arguments with integration-specific data only. This is, in structured design, this is the most explicit and the most compact way of sharing information between the modules. Data coupling. So overall, these levels reflect how much implementation details are shared across boundaries, from content coupling, in which implementation details are used for integration, to data coupling, again, where we are minimizing our integration interfaces so that we can encapsulate our implementation details as much as possible. Now, these levels were introduced in late 60s. In the 90s, Miller-Page-Jones proposed another model for evaluating coupling, and this one is more adapted to the object-oriented programming paradigm. He called it Kinescence. This word comes from Latin, again, and it means having been born together. According to Miller, two components or two things are defined as born together if a change in one component requires a change in another one, or if you can postulate a reasonable change that would require both components to change. Now, again, this change should be reasonable, something that is actually needed or might be needed in the future. Now, compared to structured design, here we have a bit more levels. And they're categorized into two types, static kinescence and dynamic kinescence. Let's start with static kinescence. These levels can be analyzed just by reading the code. They reflect compile time dependencies. And the lowest level here is kinescence of name, which means simply two variables, they need to have the same name in order to reference the same thing. For example, passing named arguments or simply referencing a variable. That's kinescence of name. Now, the next level, kinescence of type, it's pretty much the same as name. It says that in order for the integration to work, we need to know the type of the variable that we are using. So that's probably pretty common nowadays. We need to know both the name and the type. So that's why people say that both name and type, they go together. So again, if you need to know whether you should pass an integer or a string, because otherwise the integration is not going to work, that's kinescence of type. Kinescence of meaning happens when conventions are used to assign meanings to values. A trivial example here would be this example on the right side. Status equals 7. What that 7 means? That knowledge, it has to be duplicated, both in upstream and in the downstream components. They have to agree on that meaning of that value. So that knowledge is being duplicated between the integrated components. Next one is Kinescence of Algorithm. And this one happens when two modules have to agree on the use of a specific algorithm in order to understand each other. And a trivial example here is when two components are communicating by exchanging encrypted data. They need to use the same algorithm for encrypting and decrypting that data, because otherwise the integration is not going to work. So that's Kinescence of Algorithm. Now, I want to reiterate, this level is all about two modules having to agree on the use of a certain algorithm. It's not about duplicated business logic, because it is often confused for that case of duplicated business logic. Believe me, if it would be about duplicated business logic, it wouldn't be a level 4 out of 9. It will be a level 9 or 10 or 11. Anyway, we'll get there. Finally, the highest level of static kinescence is the Kinescence of Position. This one means that instead of passing values by name, they're communicated as an array where the meaning of each value defined by its position in that array. It sounds crazy, to be honest. Luckily, we're not doing it that often nowadays. One example that I can think of is, think of send email method. And it receives 4 arguments, and 4 of them of type string, from, to, subject, and body. Now, the place you put a variable in the argument list defines how it's going to be treated by that send email method. If you make a mistake there, and it's easy to make a mistake because the types are different, you are getting Kinescence of Position. So these were 5 levels of static kinescence. These are compile time dependencies. Again, they reflect how explicit or implicit an integration interface is. And again, I want to remind you, no need to try to memorize all this stuff. You don't need that. The second type of kinescence is the dynamic kinescence. These levels can be identified by examining the runtime behavior of a system. In other words, if static kinescence was about reflecting compile time dependencies, now we're talking about runtime dependencies. And the first level here is the Kinescence of Execution. This one simply means that you have a number of methods or actions that have to be executed in a specific order, one after another. If by mistake you execute them in a different order, the system is not going to work. Typical example here is working with a database. First you open a connection, then you begin transaction, then you execute a query, then you commit transaction or roll it back, and then you close the connection. This is the exact order of those operations. So they're kinescent by execution. Next one is Kinescence of Timing. Here we have an operation that should be executed in a set period of time after something else happens. Going back to the example of working with a database, let's say we have open connection method and timeout a connection method. So we open a connection, nothing happens for, say, 30 seconds. It has to be timed out. So we have to call it timeout connection method. That makes them kinescent by timing. There is a dependency in terms of time. After what period of time the second method has to be executed. Almost the strongest level is the Kinescence of Value. And here we have values that have to change together, meaning that there is a business invariant or a constraint or a rule that dictates that you have a number of values that have to change together or otherwise the system is going to be in an incorrect state. A simple example here would be a data structure representing 3 edges of a triangle. If we modify the value of one of the edges, we have to modify the other 2 as well, because otherwise the triangle is not going to be mathematically correct. So that makes that data structure Kinescent by value. And finally, the highest level is the Kinescence of identity. And here we have 2 objects that must reference the same instance of another object in order to function properly. A trivial example here would be 2 modules managing the same set of data in the same database. The database that stores the data, it has to be shared between those 2 modules, because otherwise, if each one of them is going to have its own local copy of the data and it's not going to be synchronized in any way, well, again, the system will end up in an incorrect state. So in that case, when 2 modules need to work with the same set of data, they are Kinescent by identity. So these are the levels of dynamic Kinescence. The lowest one is execution, in which operations simply need to be held out in a specific order, and the highest one is identity, in which a third object or a memory space is shared between those connected modules. Now, it may seem that we can find some similarities between the 2 models. In terms of structure design, we are going from data coupling to content coupling, and in Kinescence, we are going from Kinescence of name all the way to Kinescence of identity. Now, the thing is, it's problematic to merge these models. Because, for example, let's say I have this module that uses reflection to execute a private method in another module. Where does that put me in this structure design scale? Help me out. Come on, people. I'm using reflection to call a private method. My question is here, structure design, where does it put me? Yeah, exactly, content coupling, the worst one. What do I need to call a private method using reflection? In other words, where does it put me here on the Kinescence scale? Yes, I need to know the name. Awesome, perfect. So one model says that my code is shit, another says my code is perfect. Go figure. Now, not only that, but both models have their blind spots. For example, as I said, when 2 modules duplicate the same business logic, it is not reflected anywhere in Kinescence. And in structure design, you can say that it's control coupling in a sense, but it's not. So, you know what? And it's also not really convenient to use these models nowadays because, well, if you say, well, that microservice introduces stamp coupling or control coupling, it will definitely make you sound smart. Yes. But nobody's going to understand what you want because we are not using that terminology anymore from COBOL or Fortran, thank God. So, structure design was coined in late 60s, Kinescence 90s. That cadence of 30 years makes now the perfect time to start thinking about a new model of evaluating strength. And I want to show you something that I've been using for quite some time now. And that model has been really, really useful for me. I called it integration strength. And now is the time to start memorizing things. So integration strength combines those previous 2 models into a model that is more convenient to use. It should be more practical and more approachable. It's composed of only 4 basic levels: intrusive, functional, model, and contract coupling. As the name suggests, intrusive coupling is the highest level, and it's synonymous with structure design's content coupling. Modules are integrated through private interfaces, introducing dependencies on implementation details. When that happens, we assume that all knowledge about the implementation details of the upstream component. All those details are shared across the system, and thus we have to assume that any change to any one of those implementation details can cause cascading changes or integration issues in other components of a system. So this integration method is fragile and implicit. All knowledge is shared. Next one is functional coupling. This one means that the connected modules are implementing closely related business functionality. Its practical implication is that the same business requirements are going to trigger simultaneous changes in both components. The extreme example of functional coupling would be two components implementing the same business rule or business algorithm. If a change in that business algorithm requires the two components to change together, well, they're functionally coupled. And again, this integration method is quite implicit, because in that example of duplicating business logic, they don't even have to be connected physically to each other. This can be different microservices implementing the same business rule. And when business people ask us to change it, we have to go ahead and remember that the same rule is implemented in multiple services of that system. So again, this relationship is quite implicit, just as intrusive coupling. A lower level of integration strength is model coupling. This one means that components are based on the same model of the business domain. This level is somewhat similar to structured design's stamp coupling. We are sharing a bit more data, a bit more knowledge about our implementation details than is actually needed for integration. And again, if you have to change that model of the business domain in the upstream component, well, it's going to break the integrations with downstream components and cause cascading changes throughout the system. So to reiterate, functional coupling is more about behavior of the system, the behavior that is implemented in those connected components. And here we're talking more about data structures that are being shared between the connected components. And finally, the lowest level of integration strength is contract coupling. And here the components are integrated through an explicit integration-specific model that is decoupled from their implementation model. In other words, this integration model encapsulates the implementation model. It makes it invisible from the outside. It means that we can evolve these two models independently. We can change the implementation model without causing changes in the integration contract. So if we represent this visually, these levels reflect the amount of knowledge that is shared across components' boundaries and how explicit or implicit the integration interfaces are. Again, intrusive coupling shares the most knowledge about how the upstream is implemented. Functional coupling reduces that knowledge from how to what is being implemented. Model coupling reduces that knowledge to the model of the business domain that is being used by the coupled components. And contract coupling minimizes the interface to bare minimum that is actually needed for integration. Now, let's say that we have this intrusive coupling between two components. Does it mean that the design is necessarily bad? What do you think? Yes? Other opinions? It depends. Oh, consultants. Hey. Well, yeah, that's the correct answer. It depends. Yeah, it depends on other dimensions of coupling that we still need to discuss. And the next one is distance. And it turns out the physical locations of components, it can also affect their levels of coupling, their levels of interconnectedness. And the connections between components, they can span different distances. These distances are closely related to what we usually call levels of abstraction. We can have coupling between individual statements, between methods, objects, namespaces, components, microservices, or whole systems. Now, the interesting thing here is, what do we have on that vertical axis here? What do you think? Some ideas, shout it loud. Could you please repeat that? How strong? Yeah, in a sense, yeah, that's right, in a sense. Well, but more specifically, it reflects the coordination effort, but we'll get to that. The coordination effort that is required to implement a change that affects connected components. So if we're talking about statements in the same method, easy. If we're talking about two microservices that have to change together, we need a lot of coordination effort to make that happen. Coordination effort both in terms of development and testing and deployment, etc. All the fun things. So in other words, a cost of making a change is proportional to the distance between the affected components. The further they are spread apart, the more coordination effort will be needed. But that's not the only interesting effect of distance. And that is, the second one is a bit more related to what you said, to how they are actually coupled. And that's lifecycle coupling. As components are located closer to each other, the higher the chances that a change in one of them will inadvertently affect the other component as well. For example, if you are changing a method of a class, if you're changing its signature, probably it's going to affect other methods in the same class. But the chances of that affecting other classes are much lower. So the closer the elements are, the higher the probability of such collateral cascading changes. Now, furthermore, if components, if they share the same life cycle, which means they're located close to each other, they have to be tested and deployed simultaneously, and that further limits the possibility to evolve them independently, if that's needed, of course. Now, interestingly, the life cycle coupling is affected not only by the level of abstraction of the components, but also by the structure of the organization that implements them. Let's say an example. Let's say here on the right we have microservices. But let's consider two cases. One is we have two microservices implemented by the same team, and the second one, two microservices implemented by different teams. In the second case, we have a higher coordination effort, a lower life cycle coupling, and thus we have a longer distance between these components. So again, the longer the distance between them, the harder it's going to be to implement a change that affects both components. Now, let's say we have functional coupling, which is not really it's not the lowest one, definitely. It's 3 out of 4. It's pretty high. And we have functional coupling between two systems, which is, in terms of distances, that's insane a long distance. Is this design necessarily bad? Same question as before. What do you think? No? It depends. Yeah, both of you are right. Are correct. Yeah, it depends. So, you know what? When people tell you it depends as an answer, always ask what it depends on. So let's see what it depends on. It depends on whether the upstream component will actually have to change. Because if it doesn't change, that we're not going to feel the effects of that coupling, of that functional coupling between them over long distance. Now, how can we evaluate rate of change for a component? Well, predicting future is hard. However, there are some tools that we can use to evaluate what parts of a system are going to change the most. And here I have to wear my domain-driven design hat for a few minutes. And let's see a tool from DDD called subdomains. So according to domain-driven design, a business domain is composed of various business building blocks. These building blocks define fine-grained functionalities that are required for the company to succeed. These are, think about them as strongly related use cases. Use cases that work on the same set of data and are going to be affected by the same changes in the business requirements. These are subdomains. And we have three types of subdomains. We have core, generic, and supporting subdomains. Core is all about the company's competitive advantage. These are inventions, optimizations, or intellectual properties that differentiate the company from its competitors. This is how the company is making its money. On the other hand, generic subdomains are the solved problems. These are functionalities that have accepted solutions that you can just go ahead and use them. For example, you can buy an off-the-shelf product, or you can use an open source solution. You'll do it and your competitors are going to do it, so there's no business differentiation there. And finally, supporting subdomains are somewhere in the middle. There are no ready-made solutions, so you have to implement them in-house. However, they do not provide any competitive advantage for the company, and business-wise, you would prefer to turn them to generic subdomains, meaning to find a generic solution for those problem domains. So that means that core subdomains, they're going to be the most volatile. Business is interested in changing them the most. There is no point in changing a generic subdomain or a supporting subdomain. There is no business value there. Also, in terms of complexity, core subdomains this is where the complexity, business complexity is. Supporting subdomains, on the other hand, these are CRUD, data entry interfaces, ETL jobs, etc., things that are not really interesting. So we have these three dimensions of coupling, how we are doing time-wise. We have 7 minutes. So the interesting thing here is how we can combine them in order to balance them. The thing is, if we combine the three of them, it will allow us to estimate the pain, the maintenance pain you are going to endure by maintaining a relationship between two components. So to evaluate that pain, you need to know the strength of that connection, the distance between those components, and finally, the volatility of the upstream component. Because if, let's say, strength, it says how often downstream components are going to be affected by changes in the upstream. Distance says how hard it's going to be to implement such cascading changes. And volatility says whether you should care about that or not. It's dimension of pragmatic thinking, let's call it that way. So how do we evaluate the pain? All we have to do is my slides are stuck for some reason. Multiply them. Let's say we have a way to represent these values as numbers. Now, simplicity-wise, let's stay with a binary definition, low or high. So if the three of them are high, you have high strength, high volatility over high distance. The pain you will get is going to be high as well. Now, to minimize the pain, all you need to do is to minimize one of them, to make one of them 0. Then your pain is going to be 0 as well. Let's see some examples. If we can reduce the integration strength to the bare minimum to contract coupling, then strength is 0, volatility can be high over high distance, awesome, but these two high values are balanced out by low probability of cascading changes because of low strength. On the other hand, if strength is high, meaning that a lot of knowledge is shared between two components, and there is no way for you to reduce it to minimum, and that happens. If you have two modules implementing the same business functionality, no matter how many hoops or jumps through the air you're going to do, you will still have functional coupling. You will never get anything lower. So in that case, if volatility is high as well, and strength is high, bring them closer, so that implementing those cascading changes won't require high coordination effort. In other words, this relationship is what we usually call cohesion. And finally, if we have high integration strength over high distance, but upstream component is not expected to change, it's okay. That's, for example, let's say you are integrating a module to a legacy system. You are fetching its data from its database directly, so you are depending on its implementation details. But again, its legacy system, if you know for sure that's not going to be extended or changed, you're in a good place. You can use that database instead of trying to modify that legacy code base. And as it usually happens with legacy systems, changing them can lead you to question your integrity. Anyway, to sum it up, this is the algorithm. First, try to reduce the strength to bare minimum. In other words, eliminate all accidental coupling in terms of sharing knowledge that shouldn't be shared between components. Something that you can encapsulate in the upstream without letting the downstream components be aware of it. If all else fails, if both strength and volatility are high, reduce the distance. That's how you can balance high strength and high volatility. Now, we still have 3 minutes. Let's quickly go through an example of integration strength, because usually we say that sharing a database between two microservices is a big no-no. However, it all depends, right? It depends. So let's see a few examples. First one, let's say the component B that owns the database is not aware of that integration taking place. That's intrusive coupling. Next, let's say that they decided that they're going to use the database for integration, because otherwise they have no reasonable way to synchronize their data. We're getting here a functional coupling. That data can be used, for example, by BI department that just imports all operational data to analyze it. And they couple themselves to the model that is being used in operational systems. That's model coupling. And finally, it can also be contract coupling. For example, if that database is used for integration and it holds integration-specific data, for example, like it happens in the case of data mesh. And with that, unfortunately, I have to wrap this up because I am out of time. So again, coupling, it's an inherent part of system design. We cannot escape it. However, we can evaluate how components are coupled by inspecting how that coupling manifests itself in 3 dimensions. Dimensions of strength, distance, and volatility. And we can combine them to evaluate maintenance pain and use it as heuristic for deciding what changes we need to make to the design to reduce our pain in the future. Now, I promised that I'm not going to do a teaser for the upcoming book in case it gets published. However, I have to say a little thing that that function is going to be extended in the book. There is other aspect that is also going to be addressed in the book, but it requires me another 2 hours to cover it in a presentation. With that, I really hope I will finish it sometime soon. I have to say thank you, and if you have questions, I'll be here.